Good morning. The webinar will begin shortly. We are waiting a few minutes so that all attendees can join. The webinar will begin shortly. We are waiting a few minutes so that all attendees can join. Welcome to the third of a series of 4 webinars on the dynamic behavior of structural composites. My name is Jon Molina, and I will be chairing this session. These webinars are organized in the framework of the Marie Skłodowska-Curie Training Network Dynacom. They are taking place every Wednesday from 12 to 1 p.m. Continental Time during July. These seminars are transmitted live and will be available at IMDEA Materials YouTube channel afterwards. Registration for the remaining webinar is still open in case you are interested. Today's webinar will deal with the damage assessment of composites subjected to impact loading and is delivered by Federico Sket, senior researcher at IMDEA Materials Institute, an expert on the in situ processing and mechanical characterization of materials. The seminar will last approximately 45 minutes, and we'll have questions and answers session at the end. In case you have any questions, please let me remind you not to use the chat option, but use the Q&A section that you can see on the bottom right part of your screen. Without further delay, Federico, the floor is yours. Please start sharing your screen and start your presentation.
Well, thank you, John. Hello, everybody. Good afternoon. Just a second. I'm going to share my screen and start the presentation. So, well, good afternoon, everybody. This is a webinar that is going to be delivered in the frame of the DynaCom project, as John mentioned. And the idea of this presentation is to give a brief overview of the way the damage is evaluated in composite materials when they are subjected to impact loading. And I will particularly focus on X-ray tomography as a qualitative and quantitative characterization techniques, and I will explain how this evaluation can be carried out. Okay, this presentation is divided in 3 parts. I will start with a brief introduction about why impact in composite materials is important. Then I will cover a couple of techniques that are commonly used for evaluation of impact in composites. And following that, I will focus on quantification of impact damage by X-ray tomography and how this can be performed. So let's start with the introduction to impact in composite materials. Composite structures used in the aerospace application are subjected to impact loading during in-service condition. Some examples of threat include hailstone, lightning strike, bird impact, ice shedding or runway debris during takeoff and landing, tool drop during maintenance, etc. So in a plane, some of the different mechanical solicitation that are subjected to are indicated in this figure, which I highlighted the ones that are prone to impact. The increased use in composite materials in plane to make them lighter requires the studies of impact behaviors among other stress conditions to which composite materials are exposed to. One example of this application are turbine blades made of composite materials, which were introduced to improve the aircraft fuel efficiency as many of the composite parts in an airplane. In impact conditions, composite materials are subjected to out-of-plane loads, forces, and you probably know that composite materials have better performance in the plane where the fibers are oriented. So those out-of-plane forces, in particular impact, are detrimental of the mechanical properties. And the typical damage behaviors of a standard 2D laminate composite made up of stacking unidirectional or woven plies show the lamination between plies even at very low impact loads. And the compressive strength of the 2D laminate is then significantly reduced because the laminate is subdivided into thinner sublaminates, which might even have cracks with lower buckling loads. And so there are different strategies have been proposed by different research to improve the damage tolerance and the impact of composite laminates, including toughening the matrix, the resin matrix, 2D and 3D woven architectures, stitching and set pinning, selective interlayers, protective surface layers, hybrid materials like the one shown here in this cross-section of a tomography, in which the dark gray is the carbon fibers and the white is the glass fibers, and so on. Still, there is a lot to learn about the different damage mechanisms and impact performance of high-performance composites, and well, that's one of the reasons of this study. Okay. Here I will briefly talk about 2 common impact testing techniques for composite materials: low velocity impact testing and ballistic impact testing. This one, the low velocity impact testing, is normally carried out in a drop tower device. The sample is located here at the bottom and fixed with clamps, like shown here in this figure. And the height of the impactor is selected to have a certain potential energy and is released on the sample. Here, there is a video recorded with a high-speed camera at the moment of the impact, so you can see how the impactor leaves an indent on the composite panel. So the drop wave tower can be instrumented to measure the load and displacement on the sample, and a typical load displays the displacement curve corresponding to full penetration is shown in this figure. So the energy dissipated by the impact is computed as the area under the load displacement curve. And the mechanical response in this case is fairly linear up to the maximum load, and the ripples that appear here are due to the reflection of a stress wave back and forth because of the laminate thickness. At maximum load, the tap displacement in this case was 4.2 millimeters, and the laminate underwent already extensive damage. And after the maximum, the load carried by the composite decreased rapidly, while extensive damage developed under the tap. At this point here, there is a change in curvature of the curve, which indicates that full penetration has been achieved. And the residual load carried by the tap after this point corresponds to the friction of the lateral tap surface with the laminate. For weight critical applications, it is common to compare the dissipated energy related to the areal density, which is the ratio of the energy with respect to the density and thickness, instead of only the laminate thickness. And this is plotted as a function of the laminate thickness in this figure. And so it's possible to compare laminate architectures, laminates with different architectures, like is in the case of a carbon fiber or a hybrid material here. In the ballistic test, a gas gun shoots small mass objects, which might be analogous to runway debris, for example, against a material. The setup of the experiment is shown here in this figure, where you have a ballistic launcher, a chamber box where the sample is tested, and a high-speed camera that records the images of the impact. As you can see in this video that I'm going to play right now. You can record the moment of the impact and in turn calculate the impact and residual velocities. So when you look at the bullet that is impacting the composite material, from these couple of frames you can calculate the impact velocity and the residual velocity of the bullet when it comes out of the of the composite. This figure is an example of the damage generated by the impact test in a 2D woven composite material. The response of materials to these ballistic impact loads are analyzed in terms of the ballistic limit, or the limit velocity, which is the velocity required for a particular projectile to penetrate at least 50% of the time a particular piece of material. This figure here shows the residual velocity as a function of the impact velocity for different materials. As an example, if a bullet crashes the sample at 500 meters per second, the residual velocity of the bullet is about 400 meters per second. And as the impact velocity decreases, there is a point where there is no penetration, which is called the ballistic limit, indicated here by V0. And the calculation of the residual velocities are normally modeled by expression like the Jonas-Lambert one, shown here, where n is equal to 2 in the case of composite materials impacted by spherical projectiles. The impact energy is calculated as the difference between the initial and the residual kinetic energies of the projectile, obtained from the high-speed camera and the mass of the projectile. And again, for weight critical applications, it is common to compare the dissipated energy related to the areal density instead of only the laminate thickness. And in this plot, we have the dissipated energy related to the areal density as a function of the impact energy for different materials with different architectures, like a 2D woven, a hybrid 3D material impacted from the carbon phase or from the glass phase. Okay, this was a very brief introduction to impact testing of composite materials. So let's move on now to the evaluation of the impact damage in composite. So we know how to test the materials now, so we need to know how to evaluate the damage that is produced in the materials. So there are several techniques that can be used for impact damage assessment in composite materials. They do have their pros and cons, and here we will briefly review a couple of them with no intention to get into deep detail into the techniques themselves, which might have a lot of substantial knowledge that you need to have for that. In each technique that I put here, I put a picture of impacted specimen for you to have an idea of the type of results that you can get for each of them. The most trivial one is microscopy, in which you take a picture or a series of pictures of the damaged specimen and at a cross section. So you have to cut the material, polish it, and then take some pictures, and you will see the damage in the interior of the specimen. The other techniques that I have included here are considered in the group of non-destructive techniques, and a common non-destructive methods include infrared tomography, which uses inhomogeneous distribution of heat in a damaged sample to create an image. It's a non-destructive technique, it's fast and it's portable, but you need to apply heat to the sample, you have limited resolution, and you get information in 2 dimensions mainly. Another one is laser shadography, which is based on interferometry of shared images at the location of the defects, and in order to locate this defect, the object needs to be subjected to strain concentrations. And these defects usually induce strain concentration that are imaged by this interferometry technique. It has also limited resolution. It is considered a qualitative technique, and it gives information in 2D. You can inspect large materials as well. Among the most common techniques used in the industry is the ultrasonic testing, which uses sound waves to obtain echoes or attenuation signals as well, which can be plotted as a projection of the damage. We will come back to this later on. It's a standard technique. It's semi-3D. We will see what that means. Fast, portable, non-destructive. It's quantifiable because you get an image and you can calculate, for example, the area of the projected damage. It has the cons that if you have hybrid materials, it might not perform as you wish, and well, the saturation means that sometimes you don't have the signals because of the defect that you have in the material. Then radiography and tomography uses X-rays to obtain a map of X-rays attenuations, either in the direction of the inspection, which is the case for radiography, or in 3 dimensions, which is the case for tomography. Although I am showing here just a single cross-section, you can see the resemblance with the microscopy technique here. If you look at this microscopy figure, in the case of microscopy, this is all you get. But with tomography, this is just one cross-section out of thousands that you can get from a single scan. So you can actually have the scan of the whole sample in 3 dimensions. Okay, here I will present with no intention to go deep in this technique, the very basic principle of ultrasonic inspection, which are necessary to understand the results of ultrasonic testing, which we are going to have or show in this presentation. Ultrasound testing uses high-frequency sound waves in the order of 0.5 to 15 megahertz. The technique is based on capturing and quantifying reflected or transmitted sound waves, so-called pulse echo or through transmission modes, respectively. And the most widely used mode in this case is the pulse echo mode, because you only need access to one side of the sample. The basic principle is shown in this animation. So if a sound wave is generated, if a sound wave is generated at one end of the workpiece, it will travel through the material with the speed of sound in the material. At the free end of the workpiece, the sound wave is reflected and returns to the transmitter, which then acts as a receiver. And you get two echoes, the initial pulse and the echo from the back wall of the workpiece. Then at a place free from the effect, this is what you get: the transmission pulse and the back wall echo. When the transmitter is moved a little bit downwards, a cavity reflects part of the wave, and the part arrives earlier to the transmitter than the rest of the sound wave, and you will have echo from the defect and echo from the back wall. Even further downwards, the cavity reflects the complete ultrasonic pulse. On a computer monitor, the intensity is being plotted on the y-axis and the time on the x-axis. For material testing, either the echo of the defect can be utilized. This is the pulse echo mode, or the phenomenon that hardly any sound wave pass through the imperfection, and this is called the through transmission mode. In a pulse echo mode, the transducer is installed in a probe, and a probe performs both the sending and the receiving of the ultrasonic pulse. So here there are the parts of basic ultrasonic device, and if you know the velocity of the sound waves in the material, the travel time can be converted to travel distance. So at this point, without getting much further into the theory, we can talk about the ultrasound data presentation. Ultrasonic data can be collected and displayed in a number of different formats. The three most common formats are known in NDT as A-scan, B-scan, and CSCAM presentations. A-scan displays the amount of received ultrasonic energy as a function of time, and this is the signal that you get, is amplitude versus time. For a single position of the probe, you can get either the echo from the point A. If the probe is here in this position, you will get the echo from the defect B. If the probe is positioned at this point, you will get the back wall echo or the position C. The B-scan presentation is possible for automated linear scanning system, a scanning system that moves from this position to this position, for example. And it shows the profile of the specimen by plotting the different A-scan signals in a different type of graph, like time, depth, and scan distance versus scan distance. And this plot will correspond to this cross-section of the specimen. So by plotting the time, that can be converted to depth if you have the sound speed in the material. If you plot the depth as a function of the scan distance, you can have approximate linear dimensions in the scan direction of the workpiece, and the size of the effects can be determined. So in a CSCAM presentation, this is a type of presentation that is possible for automated two-dimensional scanning system that provide a plane type view of the location and size of the test specimen features. The CSCAM presentations are produced with an automated data acquisition system, such as computer control immersion scanning system, which is shown here in this picture. So when a probe is scanned, is scanning the sample and following this scanning pattern, for example, and a defect is found, the probe moves here back and forth and in the plane as well. And if you see it from the top, it follows this scanning pattern. When it sees a defect, or when you get an ultrasonic echo from the defect, then this will be shown in the CSCAM presentation data, which it looks like a top view of the defect you have in your material. So these are typical CSCAM CSCANs in impacted composites. Normally, a CSCAN is presented as a 2D view of the reflected echo, and the position of the defect is observed in the XY plane, which is this one. In this case, these are CSCANs of unidirectional prepregs and woven fabric investigated within the Dynacom project. The specimens are impacted with different energies using a drop weight tower, and a CSCAN provides the extension of the delaminated area in all the plies. The different architectures of the materials lead to different damage extensions and under the same impact loads. And however, this visualization, the CSCAN provides very good information of the extension of the damage. Is fast, and it's reliable. However, the visualization in this case does not provide information on what is occurring in each interface of the composite materials. We don't know. What we see is the largest delamination wherever it is in the interface of the laminates. But we have seen that at every point in a measurement in a CSCAN or a B-scan, we have information about the A-scan. And we can maybe use this information in the next slides. Before that, for quantification of the projected delaminated area, one normally use thresholding operation of these CSCAN images. And you can do that for every energy, and you can see the evolution of the projected area as the impact energy is increasing. However, the area of the different interfaces is missing, and you only get the projection of the damage area. But the energy used in the impact is used to create the cracks at the different interfaces between plies. Considering this and taking into account that we have a scan in each point of the CSCAN, we can obtain a sort of volume of the damage if we use slightly different configuration of the CSCAN parameters. This is what I wanted to show here. And if this is performed, in a sense, we have a third dimension corresponding with the depth of the composite panel. Let me see. I want to play this video. And if we plot all this information that correspond to a CSCAN, we have at every frame of what we have at every frame of this video is the time at which the echo has returned to the receiver, which is proportional to the depth, as we saw. So I will go through the video again. So we have at this top phase, this is the initial pulse. And then as we get into the material, we have information about the different impacted, the different the laminations that we have inside of the material. So in a way, this is volumetric information of the sample itself. And what we have here in the back, this is the back face of the composite material. So if we extract a plane perpendicular to the screen in this case, we obtain a B-scan, and a line across the B-scan corresponds to, well, in this B-scan you have the different delaminations shown as a function of depth. And if we plot a line along the B-scan, we get back the A-scan at this particular point, which is going to be somewhere here. But in order to present it in a 2D view, we can also project the information that we see in this Cscan volume into a single plane. And it will look something like that. And the gray levels of each delamination correspond to the depth at which the delamination is found, because the reflected intensity, the reflected pulse have different intensities as the pulse get into the material, because it attenuates when it travels in the material. However, due to the superposition of the different effects, well, you have less and less intensity, and it is difficult to observe information from superimposed delaminations here. And this takes us to another technique, which is called Xray tomography. So far we have a brief introduction to impact testing of composite materials. We have seen a standard technique which can provide information in 2D or semi-3D of the damage from impact in composite materials. And now let's move on to the evaluation of impact damage in composite materials by X-ray tomography. Okay, first let me explain in a few words the working principle of the technique. All the tomography inspections in these projects were carried out in a Nanotom 160 nanofocus. The device has an X-ray source, which is here, that generates X-rays. This is the typical X-ray spectrum of an X-ray tube. The sample is illuminated with X-rays while it rotates, and radiographies are recorded in an X-ray detector at different angular positions. We take about 2,000 radiographies, and the tomography reconstruction is then carried out from these radiographies. Due to the geometry of the setup, which is in this case a cone beam geometry, it is possible to have magnification of the images as a function of the relative distances of the sample to the source and to the detector. The magnification can be calculated simply by this formula. Okay. This is a typical, let me go back a little bit here. This is a typical data that is obtained from Cscan. It is a digital volume which contains the 3 dimensions. It is possible to look at any cross-section. You can create any plane here going through the material. And in this case, we see not only information from the damage that is generated by the impact, but also from the microstructure. So you have the dark gray plies or composite material plies. The white ones are glass fibers plies, and so on. And notice that in this particular sample, these two types of materials are very well determined here. So this is the type of information that we can get. So in this case, what I'm showing is cross-section. I present cross-sections at the middle of the impact position of the sample. And these are the same samples that were measured by ultrasound, taking advantage of the non-destructive test characteristics of both techniques. This set of images corresponds to a unidirectional pre-peg architecture, this one on the left. And the one on the right is a woven fabric architecture. In both cases, damage is observed in the form of delamination, matrix cracking, and even broken plies that we can observe somewhere here. And it is interesting to notice the more ductile behavior of the woven fabric compared to the unidirectional one. So these scans were taken at a relatively low resolution, around 25 micrometers per pixel. But even in this case, we can zoom in into a certain part of the volume and take a look at how the damage is distributed inside the material. The more rough delamination surface that we see here, how it goes zigzagging in the unidirectional prepregs is due to toughening particles that are in the matrix, while in the case of the woven fabric, the delaminations follow a profile defined by the ply interface. Therefore, you can see these ondulations. So I show here just for comparison results from ballistic tests in which the bullet was impacted here in the center. What is this possible to observe here is how the damage extends beyond what it was found for low velocity impact specimens, indicating a change in the formation mechanism. I will not enter in detail here, but let's see how we can visualize or evaluate this damage. So if we take a tomographic volumes and perform some segmentation of the damage, which is seen in a different gray level, as you saw here, this is mainly black, so we the black and we plot it with a yellow color. We can observe how the damage expands in the interior of the laminate at different depths. But if we want to take advantage of all this information contained in a tomographic scan, we have to find a way to extract at least the lamination damage from the different interfaces. So let's focus on that and not the ply crackings, for example. So one way to do this is to turn to image processing procedures. For example, the damage at different interfaces can be segmented and plotted in 3D, as we just saw. This is the segmentation of the damage from the interior of one single slice, but you can do that for all the slices and you get the volumetric information. But to separate the damage at the different interfaces, knowing that we have a deformed surface here of the composite material is not really simple. So in this approach, we use a distance transform method, which applied to, we can, I will have to explain a little bit what is a distance transform. This is a transformation in which you calculate every point here the shortest distance to the upper border of the samples, and this is then plotted as it's given a color to this distance. So what you have here is a profile that follows the upper border, and every point here is every color here indicates a distance to the surface. If we use this information of the segmented damage and we color it with the distance map calculated from the top in this case, then we can obtain this damage that indicates the different colors, indicates the different distances from the top position. And knowing that this material is made up of plies, plies that have different thicknesses, we can somehow evaluate the volume, the area, and so on of the different interfaces which are at different distances. This procedure works well for samples that have underwent low deformations, mainly because when the impact energy is high, the bottom part of the samples have larger deformation than the top part, and this is observed in the histogram here, which corresponds to the information of the pixels as a function of depth. So what you have here is peaks that correspond to the different damages. But as you go deeper into the sample, you see that the different peaks overlaps, and this means that the information of the damage at the bottom of the sample is overlapped in this histogram. So it's difficult to extract then at least this part of the damage to separate it from the laminations at different plies. So one possible way to sort out this problem is by looking at the sample geometry itself. So and try to take advantage of this. Here there is a cross section of the position of the impact, as we have been looking at, and I have enlarged it here. And if we want to select the delamination at this position, I can draw a region of interest that is called that, and extract the information of the damage from this region from this cross section. But what happened at other cross sections? So if I keep the region of interest, but I move through the different slices of the volume, I see that this region of interest, it only works when I'm at the same slice where I draw it. But when I move different slices, it does not contain the information I want. This is because the specimen has a clear bump at the impact position, which precludes me to use the same ROI for the delamination selection at every cross section. Well, one way to go around this problem is to take a look at the volume from a different perspective. Let's say we take a look from the top of the sample. This is a cross section at any middle position will look like this. So remember, here we're still working in Cartesian coordinates. So we have X, Y, and Z position. That's the Z axis. And here we have the center of the impact. So if we select the center of the impact as the center of a polar transformation, and if we perform this operation in this slice, it will look like this. So we take the radius, and this is the angle, and a polar transformation of this slice looks like this, where the horizontal axis corresponds with the radius to the center of the impact, and the vertical one corresponds to the angle position. So every line here is plotted at this position. So we can repeat this operation for every XY plane or every Z position, and get the transformation of the whole volume into polar coordinates. And these polar coordinates this can be viewed from a different angles. We obtain something like that, in which here we have the impact center, the radius, and when we go along the different slices, what we'll get is different angles of the same volume. So let's take a look at this volume along the theta axis, which goes around the impact center. And let me draw a region of interest, selecting the delamination at an arbitrary interface that I want to. And we can observe that as we move along the theta axis, the interface remains with the region of interest that I draw at the beginning of the slide. So with one single region of interest, I can extract all this information from this arbitrary interface, or for any interface for that matter. This can then be segmented and extracted in a volume of only the damage. And this is what is shown here. The damage at each interface is extracted in this way and then further quantified in volume, area, connectivity in a separate way. So here there is a comparison between the Cscan quantification of projected damage and the real delamination area obtained from the polar transform methodology just explained. So the difference, so for example, for the 40 joules, the projected area is about 14.5%, while when you take the area of all these delaminations, you get about 28%, which is twice larger in this case. And it's around 2.5 times larger for the 60 joule impact test. Even more, while the Cscan shows a constant evolution with energy, the data extracted from XCT clearly shows a steep slope at the analyzed impact energies. At some point, I imagine this should somehow saturate, but what you see here, if you take a look at the damage distribution in the interfaces, you see that there are two different quantification methodologies, the ones with the distance transform and the ones in polar transform. And what you see that first, the differences or the error between these two methods is larger at the bottom of the sample because of the distance transform method, but also that the damage distributed in each interface is larger at the bottom interfaces, and there is some contribution from the lamination at the top interfaces, but this will clearly change as the impact energy is increased. So I hope this shows the potential of the analysis methodologies explained here in this presentation. Some very short conclusion. Image processing is a powerful tool to extract quantitative information from impacted specimen. Non-destructive techniques like ultrasound, radiography, XCT, tomography, xerography are complementary techniques providing different informations, different versatilities, measurement speed, etc. applications themselves. And XCT provides the most precise data for proper understanding of the impact damage mechanisms because it gives real three-dimensional data that correspond not only to the damage, but also to the microstructure. And well, that's it. And thank you for your attention. If you have any questions, I will be happy to take them.
Okay, thank you very much, Federico, for a very interesting presentation on the assessment of damage in composite materials subjected to impact testing. I remind the attendees that you can post your questions in the Q&A section that you can see at the bottom right part of your screen. And I will be transmitting these questions to Federico, who will be answering them live. Actually, we have already a question from Kenneth Serdan Gomez. He's thanking you for the presentation, and he has a question related to the ultrasound technique. There are actually two questions. One of them is, what is the minimum damage length that can be detected? And the other one is whether this can be done in different environmental conditions, as for instance, high temperature.
Well, thank you, Kenneth, for your questions. In the resolution of the ultrasonic technique is mainly related with the frequency that you're using for the inspection, or the wavelengths, which are related. And normally it is said as a rule of thumb that the wavelength that you use, that the detecting defect, or the defect size that you can detect, is about 0.5 of the wavelength. So it's going to be in the order of the hundreds of microns. And the second question was related to temperature, right?
Whether this can be done at high temperature, the ultrasound inspection.
The ultrasound, yeah, it is possible to do inspections of ultrasonic testing at higher temperatures. Doesn't mean you can go to 1,000 degrees or so, because the probes do not stand that. But I don't know why would you like to do it at higher temperature. Normally, the electronic probes stands up to 90 degrees or so.
And it's typically done in water, right?
Well, there are two different ways to do it. There is the immersion tank. This is for Cscan inspection, but there are probes that only needs coupling agent, like a gel or something, and you can do the inspections manually at different points. So as long as it's a little bit hot, the sound wave in the material will change and so on, but I don't see why you cannot do the inspection at high temperatures. I've never done it though.
Thank you. Well, Kenneth, if you want to add anything on why you would like to do this at high temperature, please feel free to add a comment on the Q&A section. I have a question myself regarding the ultrasound testing and the possibility of extracting from the CSCAM information about the depth of the defects. You gave a very nice overview of how you can extract this information. Have you done any comparison between the information that you get in the CSCAN regarding the depth of the defects and the one that you obtain with the X-ray tomography?
Yes and no. I have done it for another project, not particularly for this one, but the depth in ultrasonic testing. So the first thing you have to take into account is that the resolution that you can get in tomography is usually larger than the one you can get from ultrasonic testing. And it is possible to obtain the information through the thickness of a sample, but the location, when you start to having reflections back and forth in different planes and so on, and you're changing the material, because you're going from composite material to air, you go composite material again. So you don't have the same speed as if the material is a block, a solid block, because you're changing phases. And that means that you will have delays in the waves back and forth. So that is why I said it's a semi-3D. It gives a semi-3D information because you have to account for the different speed of the sound wave when the material needs to go through different phases. That being said, you can see interfaces in the different due to the different plies. You can see the defects, and well, this gives you actually very interesting information about that with a very simple technique. So these waves that these gray levels that you have here correspond to the different interfaces. But this inspection needs a certain changing of the parameters of the ultrasonic testing devices.
Okay, understood. We have a follow-up here from Kenneth on his interest on applying the technique at high temperature, and the reason is work on self-healing polymers based on thermoreversible covalent bonds. So I can see now why he was interested on that, because he can produce the healing of the material by applying temperature. So it would be really nice to be able to detect these healing mechanisms by CSCAN or by ultrasound inspection as he applies the high temperature.
Okay, well, I see some complications with that. The best I could take a look at infrared thermography, because infrared thermography, it uses temperature by default, and heating the sample. When you heat the sample, and if the material self-heals, I can imagine it will change the microstructure, and it will probably give you a different picture of what is going on. Another way to do that is with radiography or with X-ray tomography, but these equipments are probably less available, or you need to fabricate in situ device or something like that. Okay. But infrared thermography could be an interesting way to go for it.
Okay, yeah, that sounds just something interesting. You mentioned in situ, and actually I have a challenging question. I know you do a lot of in situ characterization. What about in situ characterization of impact damage? Is that gonna be ever possible? Because what you have been showing in the seminar has been post-mortem damage, but sometimes how this damage evolves during the deformation provides useful information. So do you think this will be viable? Is it at the moment? Do you think it will be in the future, considering the velocities that take place during the impact?
By tomography, I don't see yet a possible application of it. Because the sample needs to rotate during the acquisition, and this could be very complicated. By radiography, yes, I think it could be possible, maybe looking at a certain angle with different types of sources. So you can go to synchrotron and you get really, really fast acquisition rates. But there are ways to do it in laboratory with flash X-ray tubes, they're called. But in this case, you will get more like a shadow of what is happening. So I don't see that being too much or more effective than a high-speed camera. Okay. Because it's a lab tube, and even if it's a flash version of it, then you do not have a lot of transmission in these very short times.
Okay, thank you. All right, so I see there are no more questions. So let me thank you again for the seminar, Federico, and thank also all the attendees to the webinar. This webinar will be soon available at the IMDEA Materials YouTube channel. And as I was saying before, if you are interested, there is another seminar taking place next Wednesday on the testing at high velocity of composite materials. With that, again, thank you, and hopefully see you next week. Bye-bye.
Bye-bye.